This is the beginning chemistry course. And so a lot of you may not be well versed in math, but it is important, especially in the beginning in this course. The fundamentals are like understanding significant figures and doing dimensional analysis. So I want to make sure that if you guys have questions on that, that I can show you examples so that you guys understand the rules. So go ahead and fire away and let me know what questions you might have or things that you would like me to go over.
I would like to go over section 4 a little bit. So
Section 4 of the activity?
Yeah, the activity. So math operations
right
using
here.
significant figures.
Yeah, that was the question that I think Kate was asking. So Kate, you're here. So I think this was the question you have. So you can see that these are pretty simple math problems that you can do in your calculator, but there are rules in terms of significant figures that you guys should know. So let me go ahead and go to the lecture and cover that so that you guys have the background, okay? So this right here is lecture notes in my website. This pertains to my Chem 100. It talks to you about exponential notation, okay? But I really want to talk to you guys about significant figures. And so first of all, if you know exponential notation, it's just a way of writing a number in terms of powers of 10, okay? So if you take 1 times 10 to the 0, anything times 10 to the 0 is just 1. 10 to the 0 is just 1. So if you take 1 times 10 to the 0, that's just 1, okay? 28 times 10 to the 0 is 28 because 10 to the 0th power is just 1, okay? 10 to the first is just 10. 10 to the second is just 100. So exponential notation is really a matter of taking a number and multiplying it by 10 so many times, because what you have in a number like this, for example, the mass of a penny, it's 29 followed by 20 zeros. These zeros are just placeholder. They don't really carry significant information other than the size of the number. So you can express it in terms of exponential notation. So you can write this as 295 times 10 to the 20th or 2.95 times 10 to the 22nd, because all those zeros really don't contain information. If you take 10 and multiply it by itself 22 times and you multiply it by 2.95, you get the same number. That's the whole idea of exponential notation, okay? And so this lecture notes in my website kind of shows you that when a number is bigger than 1, generally the exponent is positive. When a number is less than 1, the exponent is generally negative. Okay, so here are just a few examples of that. And here again are just a few examples of numbers that are less than 1. When you have a negative exponent, you're not multiplying it by 10. You're actually multiplying it by 1 over 10. Okay, 1 over 10 is 10 to the minus 1. 1 over 100 is like 1 over 10 to the second. 1 over 10 to the second is 10 to the minus 2. Whenever it's a reciprocal, you have an exponent that's negative. So that's what I'm showing here, okay? So you want to take a look at this in terms of understanding a little bit about exponential notation, again, because science, we deal with very, very large numbers or very, very small numbers, and our calculator can't handle them. So we have to express that same information via a technique where we retain the information, but don't write all those zeros. That's what exponential notation is. And then I want to share with you a very important thing that you guys should know, okay? And that is that if you have exponential notation, let's say I have 78600. An exponential notation of that number would be 786 point times 10 to the second. But scientific notation, which is a form of exponential notation, Scientific notation is actually the notation that I will be asking more often than not in this course. Scientific notation requires you to take this decimal point here that is implied but not shown, and moving it all the way to the leftmost digit. Okay, that's scientific notation. It's a form of exponential notation. So this number would be 7.86 times 10, and we see that we move it 4 times 10 to the 4th. Okay, that's scientific notation. Whenever you put that decimal point just to the right of your leftmost digit, that's scientific notation. Otherwise, it's exponential notation. So please keep that in mind, because I know that that is not very clear to students that are beginning. Okay, so let me talk to you guys about significant figures, because I can't go over this section right here if you don't know the rules of rounding off and significant figures. Okay, so I want to give you guys a proper background so that I'm not just talking about things that you may not catch on. So let me go ahead and do this. So this is the rules of significant figures. And the rules of significant figures basically means that when you take a measurement or when you write a number, certain digits don't have information, like all those zeros in that huge number. Certain digits are important, and that's what you should write down. That's why it's called significant figures. Okay, so the question is, which numbers are significant? Okay, the numbers that are significant are the ones that will allow you to figure out the error in your value. So let's take a look at this right here. Okay, let's take a look at that. We've got 12.000, and the question is, how many of those digits are significant? Now, some of you might say, oh, there's 5 digits that are significant. Some of you might say there's only 2. Pick another number, 0.105. How many of those digits are significant? In other words, how many of those digits actually give you important information? Again, that's what significant figures mean. How about 0.005320? Okay, how many digits of those are significant? Or 2,500, how many digits of those are significant? As it turns out, there are rules, and these are the rules right here. It tells you that leading zeros are not significant, trailing zeros may or may not be significant, but I have a trick for you, okay? It's a simple trick, and you will never forget how to determine significant figures after this particular trick. It's called the Pacific Atlantic rule, okay? Pacific Atlantic. And the way you do this particular trick is, let me do this for you. You have a digit, okay? When you have a digit like this number right here, 0.04005, okay? When you have a number like that, what you do is you put in a map of the United States. And why is this map of the United States important? Because the more weird the example, the better you guys remember it, okay? And I remember when I was in grad school, I came across this article and it made sense. So I've been teaching significant figures with this in mind ever since. So you put that number on the map of the United States, and then because it has a decimal, okay, it's got a period, you start from the Pacific. You start from the Pacific right here, and you draw a line. You draw a line right here all the way to the first non-zero number. The first non-zero number of 0.040050 is 4. So start counting from there as you go from left to right, from the Pacific to the Atlantic. All digits from 4 on are significant. So if you take a look at this, you can see that 4, 0, 0, 5, and 0, because those are all digits after 4 going from the Pacific to the Atlantic, are digits. So we have 5 significant figures for that number, okay? Easy to remember, okay? If there's a period, if there's a decimal, we go from the Pacific to the first non-zero number, and all digits after that are significant. Now, what if we don't have a decimal point, if there is no period? Then we again slap it in the map of the United States, and we go from the Atlantic. Atlantic means absent, Pacific means present. That's what I actually meant to say, not so much period, but present decimal or absent decimal. So if we take a look at 30500, there is no decimal, although there's an implied decimal all the way at the end. But the way it's written, there are no decimals. So you draw a line from the Atlantic all the way to the first non-zero number, going from the Atlantic to Pacific. All digits after that are significant. So this 30500 has 3 significant figures. Okay, so now we can see how many significant figures 12.000 has. It's got a decimal. So we draw a line from the Pacific. Our first non-zero digit is 1. All digits after that significant. It's got 5 significant figures. We take a number like 0.105. Our first, again, it's got a decimal, it's present. Our first non-zero number is 1. All digits after that significant, it's got 3 significant figures. If we take a number like 0.005320, the first non-zero number, going again from the Pacific to the Atlantic, okay, because the decimal point is present, is 5. All digits after that is significant. That has 4 significant figures. And then 2500. There is no decimal, it's absent. So we go from the Atlantic, going from east to west. And when we draw that line, you can see it down here, our first non-zero number is 5. So everything after that is 2. So you can see how easy it is to figure out the number of significant figures. And that's what you have right here. That first 1000, well, there's no decimal. So you draw a line from the Atlantic, the right, all the way to 1, and all digits as you go from right to left is significant. There's only 1. 1 has no decimal, but it only has 1 significant. If you take a look at 67,000,000, no decimal. So as you draw your line from right to left, the 7 is the first non-zero number. 7 and 6 are significant. So I hope that helps in terms of understanding significant figures. It really is that easy, but there's more to it than that. Okay, there's more to it than that, because you guys now need to understand how to use the mathematical operation and then round off your answer. Okay, so if you guys have questions as I talk about these things, please just chime in, because sometimes it is difficult. It's very difficult to really learn things on your own. That's why I like doing the Zoom session, because then you can get a better feel for something. So let me go ahead and talk to you guys about addition and subtraction and multiplication, division, because once you understand that, and then the section on part 4 of the activity will be really clear. Okay, let's say I'm taking these numbers, 6.2 times 10 to the second plus 2.3 times 10 to the third, and we work it out. And when we work it out, what will happen is that you get a number in your calculator. Unfortunately, the number in your calculator will contain too many information. Okay, it'll contain too much information. And what you need to do is you need to take that answer and round it off to the proper number of significant figures. But how do we do that? Well, the way you do that is understand the difference between precision and significant figures. Precision has to do with how fine your measurement happens to be. Okay, how small your measurements happen to be. Significant figures just tells you how many digits are significant in that particular answer. So I'm going to go through an exercise, and you guys can do this in your mind. I have 123 and 1.2. Which number here has the fewest significant figures? Okay, and if you say 1.2 because it has 2, then you would be right. Okay, if you say 123 has 3 significant figures, 1.2 only has 2. But now the next question is, which one is the least precise? And in order to understand precision, I need to talk to you a little bit about decimal places. So let me go back and show you something on my tablet here, because that's going to be important. Okay. Let me, if I have a number 123.4568, okay, I want to first make sure you and I are on the same page in terms of understanding this. This number is to the first place. This number, however, is to the 10th of a place, because 1 over 10 equals 0.1. So the digit right after the decimal is called the 10th. Okay, it's called the 10th. 2 digits over, if you have 1 over 100, that's 0.01. So 2 digits over from the decimal is called the 100th. Okay, because 1 over 100 is 0.01. 3 digits over is called the thousands, because 1 over 1,000, 1 over 1,000, pen's not working. Okay, 1 over 1,000 is, well, you get the idea. 1 over 1,000 is 0.001. It's 3 digits past the decimal. Okay, 1 over 1,000 equals 0.001. So it's 3 digits. So this is the 10th, this is the 100th, this is the 1,000th, and this is to the 10th of 1,000. The idea is that the further you are to the right of the decimal, the smaller that increment is, the finer your precision. Okay, the finer your precision. So let's go back to this right here. And you can see that this is only precise to plus or minus 1, 123. The error on that, you could have read this as 122, 123, or 124. The very rightmost digit is going to be your uncertainty. That's where your error is in your reading. Okay. 1.2, however, is more precise because it's more fine, and that's to the 10th. Okay, so the question is, which is least precise? 123 is least precise compared to 1.2. Okay, so this exercise right here is to try to make sure you understand the difference between significant figures and precision. And again, that's important in terms of fundamentals for part 4 of this activity. So let's take a look at the next one, 1.23 and 1.200. Which one has the fewest, smallest amount of significant figures, 1.23 or 1.200? You guys should know that. It's what? Which one has the fewest significant figures?
1.200.
Fewest significant figures, less digit. Remember, 1.200 has a decimal. So we draw a line from the Pacific. The 1, the 2, the 0 are significant. So that has 4 significant figures. So it's good that you're answering, because then I can correct you. Okay. And that's important because you don't want misconception. So 1.23, they both have decimal. Okay. 1.23 has 3 significant figures. 1.200 has 4 significant figures. Okay. But which one is the least precise? 1.23 is to the 100th. 1.200 is to the thousandth. So 1.23 is the least precise because it's only to the 100th. Whereas 1.200 is to the thousandth, 3 decimal point places over. Okay. So let's take a look at the next one. 0.123 versus 0.00012. Which one has the fewest number of significant figures? What do you guys think? You can put in the chat or something.
The second one.
Second one, exactly. Right? Because it only has 2 significant figures. Okay. You're drawing a line because they both have decimal. You're drawing a line from, let me see if I have a pen. You're basically drawing a line from the Pacific all the way to 1, and then the 1 and 2 are significant because it has a decimal point present. Here, you're drawing a line from the Pacific to the 1, and the 1, the 2, and 3 are significant. So that has 3 and this has 2. But which one is least precise? That is, has the greatest error. The 0.123 or the 0.00012?
0.123.
Exactly, because it's only to the thousandth, whereas this is to the 100,000. Exactly. Okay, and then finally, the last one here, which one has the fewest significant figures, 30 or 3,600?
30.
30, exactly, because now there's no decimal point, so we draw a line from the Atlantic, because it's absent, to 3, and there's only one significant figure there. Whereas 36, this also doesn't have a decimal, so we draw a line from the Atlantic to the 6, and as we go from right to left, the 6 and the 3 are significant. So that has 2 significant figures, okay? So you got to make sure that you understand significant figures, because adding and subtracting, multiplication and division requires you to understand that fundamental. Now, which one is the least precise, 30 or 3,600?
3,600.
Exactly, because the error on this, again, the rightmost digit that is significant is the error. So this has an error of plus or minus 100. This has an error of plus or minus 10. Okay? Because the zeros in both of these digits are just placeholders. They're not significant. So where you see the non-zero number, the rightmost non-zero number, that's where you start looking at your precision. Now that you understand that, take a look at this. Suppose someone gives you some change. Okay, some panhandler is collecting money, and the first person here gives them $2.52. Okay, that's pretty precise. You can get that exact number. Another person gives them $3.26. Okay, and then another one gives them 50 and a few pennies here. Okay, now if you look at these pennies, it's very hard to figure out how many pennies you have because it's just an estimate. So the biggest error in all of these is this value right here. Okay, because you're estimating how many pennies that happens to be. It could be 20 pennies, it could be 18 pennies, it could be 26 pennies. But one of your data here has the biggest error, and that happens to be this. Okay, it happens to be this right here. So it's the same thing when you guys are given numbers to add. This is only true for addition and subtraction. Okay, if we take 5.6 times 10 to the second, that's 560. 560. But 5.6 has 2 significant figures, so the 0 here is not significant. Okay, and then you've got 2.3 times 10 to the third. If you change that to whole numbers, that's 2300. Now, what you need to do is add this up, okay? And you would write based on these values 2860. But the number with the biggest uncertainty, that is the least precise, okay, happens to be, in this particular case, 23 times 10 to the third. Why is that the least precise? Because this has an error of plus or minus 100. This has an error of plus or minus 10. So when you round this number off, you're going to round it off based on this digit right here, because that has the biggest uncertainty. You can't write a number like this, because when you write a number like this, you're saying that your uncertainty on that number is plus or minus 10. But the data that you got right here has an uncertainty of plus or minus 100. So you can't do that. What you need to do is you need to round this off to where this is plus or minus 100, and that happens to be 2900, or 2.9 times 10 to the third. Okay, that's why it's really important to understand precision in addition and subtraction, because you're always going to round off to the least precise data. The least precise data. Among these two, it's not obvious when it's in exponential notation which one's the least precise, but when you draw it out, you can see right away 2300 is plus or minus 100. 560 is plus or minus 10. Let me give you another example. Okay, let me give you another example so that this makes better sense. Let me draw it here. Let's just take a look at that activity so that I can we can we can work with real numbers. So let me change this. You guys can see. So if you take this first example right here, you got 1.0 and 3.88. Okay, you can see right away that this has an error of plus or minus 0.1 to the 10th of a place. This has an error of plus or minus 0.01 because it's to the 100th of a place. Which one is the least precise? This one's the least precise. So you're going to have to round it off based on 1.0. So when you add this up, that's 8, that's 8, that's 4.8, but it's got to have an error of plus or minus 0.1 because it has to have the data that you have with the biggest uncertainty has to also be contained in your answer. So if this is plus or minus 0.1, you can't write 4.88. You've got to write 4 point something, but then you have to round this up to 9. Now it's plus or minus 0.1. That's why the answer there is 4.9. You could have wrote 4.9 or 4.9 times 10 to the 0 because 10 to the 0 is just 1. Okay, let's take a look at another value right here. Let's take a look at this right here. Okay, if you take a look at that right there, that's 114.45 minus 20. And that 20 has a decimal. So this has an error. This has an error plus or minus 0.01. It's to the 100th of a place. This, however, has an error of plus or minus 1. This has the biggest error right here. So do your math calculation first, 114.45. And when you do that, let me just show you this calculator because I want to make sure that you guys are able to see that. Okay, so if I take my calculator and I do 114.45 and I subtract 20, this is the number I'm going to get, 94.45. But that would be wrong if you just wrote that answer, okay? Because this has an error of plus or minus 0.01 reflecting on that, but this it's got to reflect on 20 because that's your least precise value. Remember that example I showed you about the panhandler? Well, you can have a better precision on the calculated value than the greatest error in your data. And the greatest error in this data is 20. So you have to round this off to 94. That would be your answer for this particular problem, because now that would be plus or minus 1, the same as this value right here, which has the biggest error. Okay, so hopefully that makes sense. Addition and subtraction is probably the most difficult. Why? Because you have to look at the least precise and round off your answer based on the least precise. Okay, that's why it's difficult and that's why it's not obvious. Between these two right here, 5.386 and 3.11, the least precise is 3.11. Your answer needs to be rounded off to the 100th of a place, because this right here is the least precise. This is to the thousandth, this is to the 100th. Your answer's got to reflect the least precise. It's got to be rounded off to the 100th of place, 2 digits over. Okay, now let's go with multiplication and division. Multiplication and division is super easy because you don't have to know the difference between precision and you just have to know significant figures. So let's take a look at this right here. And I have 5.600 times 10 to the minus second times 2.3 times 10 to the minus 3. How many significant figures does 5.600 have? What do you guys think?
Is
Got
it
a decimal point. What do you think? 2 or 4?
2?
Got a decimal point. So you draw a line from the Pacific to 5, and O digits after that are significant. So the 5, the 6, the 0, and the 0 are significant. Okay, that's why I want you guys to answer, because I want to make sure that I correct you, because if you're answering this in your mind and I'm just assuming that you're getting it right, then you're going to get it wrong when you do the activity. This has 4 significant figures because it has a decimal. How about this right here? How many significant figures does that number have? Should be straightforward. What do you think?
2.
2, exactly. By the way, the exponential are not counted in significant figures. It's just the numerical value. This has 2, this has 4. Which one has the fewest significant figures? 5.600 or 2.3? Fewest significant figures now.
2.3.
Exactly. See, the rules of multiplication and division says that you round off your answer based on the fewest significant figures. So your answer here has got to contain 2 significant figures. Okay? It's a different set of rules than addition and subtraction. That's why we went through this exercise right here, because if you don't know the difference between precision and significant figures, you're going to get messed up on the math operation. Who would have thought that simple addition and subtraction would be so complicated? Well, in science, it can be very complicated because we're always looking at significant figures. Okay, so here we go, right here, in terms of these values right here. Okay, so I can tell you right now, among these questions over here, let me see, this right here, when you do the final calculation on this first one, your answer better contain 2 significant figures. This second one right here, your answer better contain 2 significant figures. I'm not even doing the calculation. All I know is that this is 2 significant figures, this is 4. Your answer's got to be 2 significant figures. This has 3 significant figures, this has 3 significant figures. It's a division. Your answer better be 3 significant figures. This has 3 significant figures, this has 3 significant figures. Your answer better contain 3 significant figures. Multiplication and division is actually much more simple compared to addition and subtraction. Okay, because you're just looking for the fewest significant figures. And so here's the question right here. You got 6.500 times 10 to the minus 2 times 5.5 times 10 to the minus 3, and you get this in your calculator. Okay, it's a very big number. But you know from the rules, you got to round it off to 2 significant figures. So you got to express it in exponential notation. See how there's a decimal here? You got to move it all the way right after the 3 to make it scientific notation. Then you got to round it off to 2 significant figures. So that would be 3.6 times 10 to the 1, 2, 3, 4, 10 to the minus 4. Okay, because you got to move that decimal all the way to the right, and that number's less than 1. That's why it's got a negative exponent. But now you're rounding it off to 2 significant figures. So that is basically what's going on here. When you multiply this out, 2 significant figures, 4 significant figures, you better have 2 significant figures. This right here, 3 significant figures, 5 significant figures, your answer better be 3 significant figures. Okay. So again, multiplication and division is much easier compared to addition and subtraction. So let's go back to this your activity again, so that you can see how this example applies. Okay, so let me clear everything here. Okay. So when we take a number like this right here, and you work that out, take 2.3 times 10 to the minus 3. Let me show you how that's done in your calculator, because it's really important that you guys know how to use your calculator, because if you don't use your calculator properly, you're going to get messed up down the line. So I'm going to take 2.3, 2.3. And you see this double E? You should find that in your calculator. You should see a in your calculator, a double E. Don't use this function right here. Don't use 10 to the x. Okay, if you use 10 to the x, that's wrong. You got to use double E. Now that will get you to the exponent side, and we're just going to do -3, like that. You've got to use the double E in your calculator, not this 10 to the x. 10 to the x is an exponent function. What we're trying to do with double E is just trying to express a number in scientific or exponential notation. Okay, now we're multiplying it by times 2.501. That's the number. And then we're going to hit equals. And you can see right away that that number is, let me just see, that number's rounded off, unfortunately.
Not rounded as 0.005753.
Okay, yeah, that's good. I should be able to change this so that I have more. I think I can go over here. If you have a, yeah, here. Okay, I'm going to make this 10. There you go. Okay, if you got a Mac, you've got a calculator there. You just got to be able to find how many digits to view right here. And then you can see, but that's what you would write down right here as your raw data. But how many significant figures should this number contain? Your answer should contain. According to our rules, it should have 2 significant figures. Yeah, exactly. So now we can take this, and I think there is a way to make that scientific notation. This would be 5.7 times 10 to the minus 3. Okay, 5.7 times 10 to the minus 3, because we're moving the decimal point 3 places over. And actually, it's 5.8 times 10 to the minus 3, because if you take a look at the 7 and the digits right after that, see how we have 523 right after the 7? Well, 523 is higher than 500. So we got to round off 7 to the next digit up. If this was 499, then we retain the 7. If it was exactly 500, then we round off only if we're rounding off to an even digit. Okay. So that really is what part 4 is. It's a little bit longer to explain, but I wanted to make sure I cover all the bases for you guys and not just give you the answer. I need to understand the fundamentals. Like this number right here, if you're dividing, this better have 3 significant figures. You don't even have to write it down. You know that this is 4 and this is 3. Your answer better be 3 significant figures. Now, the reason why the top number is 4 is because it has the decimal. So the 1, the 3, the 2, and the 0 are significant. Okay, so this has 4 significant figures. This has 3 significant figures. This number right here, you got 4,002.6789 times 10 to the minus 6. How many significant figures should my answer contain? What do you think?
1.
How many significant figures does 4,000 have?
Oh, no, wait, never mind.
1.
1 significant figure.
Oh, am I doing this right?
This
So it does,
digit
so
right
it
here,
does have 1.
it has 1. So your answer has to have 1 significant figure.
Okay.
Okay, because your data has 1 significant figures and 5 significant figures. The fewest significant figures is 1. In multiplication and division, you're always rounding it off to the fewest significant figures. In addition and subtraction, you're always rounding it off to the least precise. There's a difference. There's a difference. Okay. So that's why these answers are here, because you need to practice that. And the same with the operation in number 5 here. Okay. For here, we've got 3 significant figures and we've got 3 significant figures. your answer better be 3 significant figures. You're multiplying in all of this. This has 4 significant figures. This has 3 significant figures. Your answer better have 3 significant figures. This has 1 significant figure. This has 2 significant figures. Again, it's a division. Your answer better have 1 significant figure. That's why you have to know that little trick I showed you into spotting how many significant figures a number have, especially since the majority of your calculation in science is multiplication and division. Okay, but you still do some addition and subtraction. So I hope that clears some of this. Okay.
Can you go over question E, like the very last question about the pennies?
Oh yeah, that's dimensional analysis. Okay. The whole thing about dimensional analysis, let me clear this real quick, is that here, let me give you a 5-minute introduction, and then I'll show you why this thing is actually, and if there's anything that you learn in this class, especially for those of you who are going to nursing, is dimensional analysis. Dimensional analysis actually got a book to try and figure out put some questions that in the nursing field in some of my exam. But when I got this book, they said that dimensional analysis is nursing math. Okay, you do a lot of dimensional analysis in nursing. If you take a number, 28 in this particular case, okay, and multiply it by 1, then you get that same number, 28. Okay, if you take that number, 28, and multiply it by 5 over 5, 5 over 5 is just 1. So that's 28. If you take that number and you multiply it by 1 dozen over 12, 1 dozen equals 12. It's the same. So it basically gives you a number that is different. Like in this particular case, it's going to be a different number, but this is nothing more than 1. This equals 1. So 28, 12 divide, that's 2.33 dozen, but that's just with a different unit now, but you're still multiplying it by 1. That's the whole key of dimensional analysis. It's what we call a translator. You have a given unit, and then you put it through this box, and it's a translator so that you get your desired unit. Kind of like if you have, if for example, the euro is 0.96 to $1, okay? If that's the euro, then if you spend $1, if you spend $3.25 in Europe, and you're asked to figure out how much it is in euro, then you can basically do this. Okay, and again, this is dimensional analysis, the units, because one's in the numerator and the other's in the denominator will cancel. Okay, this dollar sign and this dollar sign will cancel. And what you get is the correct answer in the proper unit that you are looking for. So we can take 3.25 and we can take 0.96 and multiply and divide by 1, and that's 3.12 euros. So we basically convert dollars to euros. That's the whole idea of dimensional analysis. Okay, so the key here is the translators, So if we go back to this problem right here, what you need to do is you need to write down all the conversion factors that is available in this problem. So let's read this. How many pennies are needed? So our final answer is pennies. Our final answer here is pennies, because that's what this question is. How many pennies are needed? A penny, 1 penny is 19.55 millimeters. That's a conversion factor. Okay, it's not implied, but that's what you have to read into. 1 penny has a diameter of 19.55 millimeters. So that's a conversion factor. 1 penny and 19.55 are the same for that length. Okay, are the same for that length. It's like 0.96 euros equals $1. For that situation, they are the same. For this situation, the length of a penny is 19.55 millimeters. Okay. The second question here is you've got 18 minutes, 15 seconds. Now that's not a conversion. Okay, that's just raw data. That's how long it takes. It takes 8 minutes and 15 seconds for light to travel from the sun to the earth, and 186 282 miles. See this slash right here? That means it's equal to 1 second. In 1 second, light travels 186 282. So we're making it an equality. That's an equality. Whenever you see that slash, it means 186 282 over 1 second, and that's a conversion factor. So that's a conversion factor that you would use. How many pennies are these that you would have, and how many dollars? Basically, 100 pennies equals $1. So these are the conversion factors that I would be using for this problem. Okay, so let me kind of help you set this up. I'm going to erase all this. Okay, I'm going to erase all that so that you guys can see okay, how to set this up. So we're going to start with time. We're going to start with time, and we're going to make that seconds. Okay. Now, if you look at our conversion factor, where is seconds? It's right here. So our first conversion factor is seconds over miles. And I'm not even going to put the numbers there. I'm just going to put the units because that's the magic of dimensional analysis. You let the units walk you through the problem. Okay. Now you can see that we have no miles in our data, but you know that miles is the length. Okay. You know that miles is the length and millimeters is the length. So somehow we're going to have to take miles into millimeters. Now, that conversion factor is not easily found, but I do know that for every 1 mile, there is 5280 feet. I do know that. Okay, it's in the conversion factor that you can look up. And I do know that there are 12 inches in 1 foot. And I do know that there are 2.25 centimeters equals 1 inch. Okay, these are common conversion factors that you can look up. And then finally, I do know that there are 10 millimeters in 1 centimeter. All these are just conversion factors. And that's what I'm going to use in this problem. See how I have miles here? Well, I'm going to use this. I'm going to use that first for that. And then I'm going to use feet, 2 inches, right here. And then I'm going to use, see how I'm always making the unit walk me to the next step. Inches to centimeters. And then I'm going to go over here. And then centimeters to millimeters. And then millimeters to pennies. And that's my answer. So you just set up the problem so that the units lead you to the next conversion. And all we got to do now is convert this to seconds. So 18 times 60 plus 15 seconds, that's going to be the time that we're going to be using because we want everything in seconds. So I'm just going to take 18 and multiply it by 60 and then add 15 to that. So that comes out to be, let me make sure that I'm doing this correct. That comes out to 1095. Okay, so that's what you guys have to start with. When you can, because your conversion factor is seconds here. So you can't use minutes. You got to convert it to seconds. So take 18, multiply by 60, and then add 15 to that. Now we can just let the dimensional analysis worked its magic. We know that for 1 second, it's 186, 282. You know that for 1 mile, it's 5280. I'm just writing now the values associated with each unit. For 1 foot, there are 12 inches. Okay, right here, 1 foot is 12 inches. For 1 inch, there are 2.25 centimeters right here. For 1 centimeters, there are 10 millimeters right here. And I know that for 19.5 millimeters, there's 1 penny. That's the magic of dimensional analysis. When you really get good on this, it'll save you in stoichiometry, which is like chapter 7. And when you're
Can
really good at this,
I ask a question really quick?
sure.
You're saying 1 inch equals 2.25, but I think just confirm it's 2.54 for me.
Oh, okay.
Is that correct?
Yeah, you're right. It is 2.54.
Okay. All right.
You're right.
I was gonna.
Okay.
Okay. Thanks.
You're
That's
right.
all.
I got that. I don't know where I got 2.25.
No, that's fine. Okay. Keep going.
But yeah, you're right. That is the correct conversion factor. So change that. But that's dimensional analysis. If you know how to do dimensional analysis, it's going to save you in a lot of the problems because we don't give you equations. You just let the units work the magic. Okay. And like I said, one thing that will save you in college is if you understand how to work dimensional analysis. That's why we took this problem, which has no equation, but we use dimensional analysis to solve it. Okay. Same thing here. Okay, this problem right here. How fast is a car moving in centimeters per second if its speedometer 65 miles per hour? Well, if its speedometer 65 miles per hour, okay, that's basically what 65 miles per hour is. And what we want to do is convert this to centimeters per second. So the length has got to be on the top, time's got to be in the bottom. So you guys know how to convert hours to minutes, minutes to seconds. See, I'm not even writing the numbers because I will fill that up later. All I'm doing is I'm allowing the units to walk me through. I'm allowing the units to set up the next conversion factor. And then I'm going to convert miles to centimeters. And I do that by doing this. Miles on the bottom now, because remember that miles in the original data is in the numerator. The top is numerator, the bottom is denominator. So the units, in order for it to cancel, it's got to be in the denominator in your conversion factor. It's got to be up and down in order for it to cancel out. And I know from the previous penny example, I know the relationship between miles and feet. I know the relationship between feet and inches, and I know the relationship between inches and centimeters. And then all I got to do is put in the values here. I know that there for 1 hour, let me change my pen. There's 60 minutes. I know that for 1 minute, there are 60 seconds. I know that for 1 mile, there's 5280. And I know that there for 1 foot, there's 12 inches. And I know that for 1 centimeters is 2.54, okay? And then all I got to do is the math. And let me show you real quickly how you would do this in your calculator. Because too many times you guys take too many steps in your calculator, okay? And when you take too many steps in your calculator, then you can get error, punching in error. So the way you would do this, let me clear this real quick, is you first take 65, oops, 65, so you can see what I'm punching in, and then divide by 60. That's the first step. So I'm going to press divide. I'm going to do the 60, and then divide by 60 again, because it's in the bottom. I'm not even hitting the equal sign. And then multiply by 5280. And notice I'm not doing anything with the 1. because any number multiplied by 1 or divided by 1 is the same number. So I'm skipping that step. Okay, and then multiply by 12, and then divide by 2.54. And then you hit equals. Okay, so when you punch it in your calculators, eliminate the tedious step of multiplying by 1, dividing by 1. Just go straight to how you set it up. You just go 65 times divided by, because the first number is divided by 60, divided by 60, multiply by 5280, multiply by 12, and divide by 2.54. That is the fastest way of punching it in. Don't spend time multiplying by 1 and dividing by 1. It's a waste. When you multiply by 1, it's the same number. When you divide by 1, it's the same number. Just go through the operation and you'll get your answer correct. But these are little tricks that will save you time and punching errors. Does that kind of answer your question in dimensional analysis?
Yeah, definitely. Thank you.
Okay. So, yeah, I appreciate you guys attending. For the few of you, 5 of you who are here. Hopefully, you're getting something out of it. Okay. Any other questions? We're already well into the hour. If there are no questions, you can always fire me an email, and I will.
I just have a quick, just to confirm about how to submit it. So, I'm doing them all by hand, and then we're
You're doing it by hand. Then when you go into Canvas, let me just show you real quick. When you go to, this is it. Go to the module page, and then you go to this right here. If you have everything set up, just make sure I'm on the right. Yeah, this is the lab. So you go right here, and then I'll do a preview here. So here, to the 100th of a place, 21.46, okay, 46, right? Because this is 499, okay? So you're not rounding up. When you're thinking about rounding off, look at the whole digit after. The 100th place is 2 digits over. So the next digits after that is 4, the 9, and the 9. The 499 is lower than 500. So you retain this 6 right here. Now, if this was 501, then you would round this up to 7. And these are basically the same numbers in your activity. Okay, round off to the 10th, 482.5. You're rounding up now, right? Because 506 is higher than 500. So you got to round the 4 to a 5. So that's basically what these are. How many significant figures there? You guys should know that's 3, right? How many significant figures here? You guys should know that as well. Okay, here you want to put down what your answer should be, and here what your raw data is and what your correct answer should be. That we went over this today. Here's the same thing. You just want to round off your answer based on the number of rules of significant figures. And then these right here are just conversion. And what you want to use the appendix value, okay? Don't use something else, because your answer are based on that appendix. And then this right here is just your answer based on the dimensional analysis. So you're just uploading your worksheet, but putting your answers here as well. Okay, I think you get an extra 2 points if you do your worksheet. Does that answer your question in terms of that?
Okay, yeah, so we're just putting in all of our work here, and then there's a separate,
Yeah, the very last
you're
question is an upload. You click on this right here, that very last question.
Mhm.
You click on that, it'll, let me go as a student, because as an instructor, I don't see that. You click on Start Assignment right here. That's what you will see. And then just find your file and then upload it. And then you're done.
Okay.